All right, what we are looking at today is your enthalpy, stoichiometry, and Hess's law worksheet. What we have right here is your first question. So to the right, we see our enthalpy. Remember, this is going to be our conversion factor that we are going to use. I know your worksheet doesn't have it, but it really should. Moles of reaction is what we should have on here. All right, so we want to calculate the quantity of heat when we have 5 grams of sodium bicarbonate that reacts with excess. The excess is just something we don't need to worry about, so we are focusing on this sodium, I meant to do a highlighter, sodium bicarbonate, which is this thing. So we are going to start with our measurement, which is our 5 grams of our NaHCO3, and that's going to be the start of our stoichiometry. Before you even start thinking about conversions, the unit grams is at the top. It's going to automatically go to the bottom. Now, what we're trying to do here is convert from our sodium bicarbonate into our heat. So we know that we're going to have to go through moles. So our first goal should always be to get to moles of our compound. I'm going to assume that we're doing pretty good with our molar mass. If we are not, please come and see me so we can go over it. If you are feeling confident with your molar mass, I am A-okay on your homework if you are Googling the molar mass. A lot of times the AP chemistry test will give you the molar mass, but sometimes they will ask you. So if you are not sure, make sure you are still calculating it and double checking yourself. You should get around, 84.01 grams. I have grams at the top, grams at the bottom, so they're going to cancel out. If I have moles of NaHCO3 at the top, I'm going to have moles of NaHCO3 come to the bottom. Remember, only the unit and the compound come with us, not the number. So I now have moles of NaHCO3, and again, our goal is to be able to use our conversion. And what this represents is the amount of moles in my entire reaction. So for one pass of this reaction, I'm going to use 3 moles of NaHCO3. And I know that because this balanced equation, in one balanced equation, I have 3 moles of my sodium bicarbonate. This is going to allow me to cross out moles of sodium bicarbonate, and it leaves me in moles of reaction. So again, before I even start thinking about the conversion, if I have moles of reaction at the top, then I'm going to have moles of reaction at the bottom. And what this conversion factor here is saying to me is that for every one mole of this reaction, it produces 70 kilojoules. And so moles of reaction then cancel out. So this is my completely set up ladder. If you are not including your units, you're doing it wrong. If you're not including your compound, you're doing it wrong. Remember, our goal is to show our work in such a way that the reader, who is human, has no concerns about exactly what you did. All right, so now we're going to multiply the top. So we're going to do 5 times 1 times 1 times 70. That should give you 350. We're going to multiply the bottom, 84.01 times 3. That's going to give you 252.03. And if we divide those two, you will get 1.39. Now, what's our units? Look at that constant. That constant that we just used is kilojoules. So our answer is kilojoules. Look at what you ended with there, kilojoules. Now, this particular question did ask for joules. We're going to bounce our decimal 3 places. Remember, your King Henry died by drinking chocolate milk. And so this becomes 1,390 joules. Let's check our significant figures. If that's something you're interested in, that has 3. We're only focusing on this value for sig figs, and this has 3 as well. All right, so for our second problem here, instead of starting with a mass of our reactant, instead it's asking us how much of something do I need, how much will be produced with a certain amount of heat. Our setup is going to be exactly the same. We're just going backwards. So in A, I went from grams to kilojoules. This time I'm going to go from kilojoules to my grams. And I should put my decimal for my sig figs. Again, before I think about anything, I have this unit at the top. Automatically, I know that kilojoules is going to go to the bottom. The only connection I have to kilojoules right now is my delta H, my enthalpy. So I know that that is 70 kilojoules for every 1 mole of reaction. My kilojoules cross out. I have moles of reaction at the top, so I need moles of reaction at the bottom. And my goal is to go from kilojoules to grams of carbon dioxide. So my goal is to get to CO2. Remember, the only time that you can change from one compound to the next, or in this case, from reaction to another compound, we have to be in moles. So if I look for every one of these passes of reaction, I can see based off my balanced equation that I have 3 moles of CO2. Moles of reaction cancels out. And my moles of CO2 is going to drop to the bottom. My goal is to get to grams of CO2. Again, if you're having a hard time with molar mass, please make sure you are attempting it. If not, it is 44.01 grams of CO2. My moles of CO2 cancels out, and I am left with grams of carbon dioxide. Let's multiply the top. 300 times 3 times 44.01 is 39,609. Multiply the bottom is 70. And this gives me 565.8. And again, this is grams of CO2. Well, let's check our significant figures. I have 3 significant figures here, so my answer needs to be 3 as well. So this would round to 566 grams of CO2. Again, you do not have to be putting things in significant figure. There is one point in the entirety of the test that is significant figures, so I do not want you stressing about significant figures when you could be focusing on the other math. All right, so that's your stoichiometry. All of your enthalpy stoichiometry is going to follow this path work. All right, so we have a new equation this time, and instead of having a delta H off to the side in the form of a conversion factor, what we are seeing instead is that the energy is actually inside of the reaction. It is an actual product of this reaction. And so if I'm looking at this, it's asking, is this endothermic or exothermic? So remember that these are my reactants. They are what go into my chemical reaction. And then these things here are my products. They are what come out. So if my energy is coming out of that chemical reaction, we would expect it to be exothermic. So anytime you see energy as a product, that is exothermic. And if you see the energy as a reactant, that is endothermic. So it's asking, what is our value of delta H? This is exactly the same thing. It's just a different way of looking at it. So my value is still going to be 6,536 times 10 to the 3 kilojoules in 1 mole of reaction, because it's the same as my balanced reaction. Oh, I don't have to put that one. But we do need to put our sign when we're talking about our delta H, and we just said that this is exothermic, so we would have a negative 6.536 times 10 to the 3. All right, it wants us to draw a potential energy diagram. So my time is going to go on the x-axis, and my potential energy is going to go on the Y. So we're just going to choose anywhere that we want to start our reactants. It's going to start as a straight line because originally the reaction is not occurring. It is just staying stable. And we are going to add our activation energy. So every reaction is going to have this increase with activation energy. Now, the most important part is this last part. Where are my products? Are my products going to be below my reactants in potential energy, or are they going to be above them? This was exothermic. So that means that I need to have lower energy because that energy leaves those reactants when this graph is complete. So I'm going to draw my line below those, and I'm going to connect my line, and this will be my products. And so we can see if I were to draw dotted lines across, this would be my negative delta H, showing that it's an exothermic reaction. Again, there are no numbers associated with this. We are just showing this overall profile. All right, and then our final one that I'm going to review with you is the more challenging of the Hess's laws that were given to you. Those first two were pretty simple, and to be honest, I would almost say they were overly simple, whereas this last one is almost a little overly complicated. To be honest, I didn't give you a good example of right in the middle. Maybe I'll go fix that here in a second. All right, so if I am looking at this reaction, remember the first thing we should always be looking for is what is my total reaction? So my goal is to make these three miniature reactions to turn them into this final reaction. So I'm going to look piece by piece for my reactants and my products. So I have my H3BO3. I see it's here and nowhere else. Perfect. If it shows up in two places, leave it for the end. Don't touch it. We're looking for things that only show up in one of my steps. So between my given reaction and the reaction that I'm trying to finalize, I see that there are two here. So I need to multiply this reaction by 2. That's going to turn this into 2H3BO3, 2HbO2 plus 2H2O, and I'm going to multiply my delta H by 2, so it's going to become negative 0.04. All right, the next thing that we are looking to in our reactions is B2O3. I see, where's it at? Here it is, B2O3. I only see it in one of these steps, which is perfect, and we're going to solve for it. Now, I'll notice that here I have 2 B2O3. Here I only have 1. So I'm going to need to divide by 2, or since we could only multiply, we are going to multiply by 1/2. So that is going to turn this reaction into 1/2 H2B4O7, 2 times 1/2 leaves me with 1 B2O3 plus 1/2 water. I know that looks weird. Just leave it in there. Usually it solves itself. So we're going to do the same with our delta H. So half of our delta H, it is still positive because we did not have to flip anything. So this is positive 8.75. All right, and then the final thing that we have here are my 3 waters. And I have water in a few places. But once we get to this part, we have one step left. We don't want to touch step 1 because I have solved for my H3BO3. I have that reactant correct. So I'm not going to touch reactant 1 again. Reaction 3, I'm not going to touch that one again because I have the B2O3. So this second reaction I have here in the middle needs to solve for what I currently have left. So if I look at my first two reactions that I've changed, I notice that I have 2 waters on my reactant and then a half. So I currently have 2.5 waters. So I need another half of a water. And I need that half to be in the products. So currently in this equation, I can see that it is a reactant. So automatically I know that I'm going to need to flip this reaction. So I automatically know that this is going to become 4HbO2, and I know I'm not done yet, so don't panic on me. If you're doing this in pen, you're going to regret it. H2B4O7 plus H2O. So I've just flipped it. But I now have 3.5 waters. I only need another half. So I also am going to multiply this one by a half so that I can have the proper number of waters that I need. So when I multiply by 1/2, 4 times 1/2, that turns into 2. This will turn into 1/2 H2B4O7 and 1/2 H2O. So now I have 3 waters total, which is exactly what I want. And if I look at my delta H, I flipped the sign, so that becomes positive. When I flip, I change my sign, and I multiplied by 1/2, so that becomes positive 5.65. But I also need to check, because this I need to keep. We said this we need to keep, and we said these 3 things we need to keep. So there's a few things in here that I need to make sure that cancel out. In order for them to cancel out, I need the same number as reactants as I do products, because it basically comes out in the wash. If 2 reactants go in and 2 products come out, they did not actively participate in the reaction. They were there, and we'll talk about them later. They're either considered intermediates or catalysts, but we don't need to worry about that right now. What we need to know is that they cancel out. So we'll notice here that my 1/2 H2BO4O7 is a reactant here, and it is a product here, so it cancels out. My 2HbO2 is a reactant here, and it is a product here, so they cancel out, which is perfect. That shows me that I've done everything correctly, that what I don't want cancels out, and what I do is still a part of my reaction. Alas, we are still not done. So I now have my new delta H values for each of my steps, and I am now going to add this all together. Negative 0.04 plus 5.65 plus 8.75. This comes out to a positive 14.36 kilojoules per mole of reaction. All right. If you did this one, there's nothing that AP Chemistry is going to throw in you as far as Hess's law goes, because this was a very challenging Hess's law.